All right. So earlier this morning, we learned a lot of the big picture stuff around learning models. We also did a lot of work to get our environments for working with PyTorch set up, from digging into Python virtual environments and getting Jupyter notebooks set up, which is what we will be using really next week for all of next week, um, along with some other things. Um, we talked about how neural nets work, a bit, how learning models work, and we saw PyTorch, which is a library for building learning models and doing lots of really interesting sort of numeric calculations with Python. And just as a reminder, we set up our Jupyter notebook file here where I can add cells of markdown or code, and also see them rendered in the same file, which is great, right? And I can modify this and I see my code run. And as our test, we tested that Torch is installed and now we will use it. And just to take a look at an example of where we'll be going and kind of how this, what we're about to learn will relate. Um, Let me just show one of these data sets. And binary classification. Someone want to remind me just very briefly, like what binary classification is?
It takes a result and classifies it to either a thing or not a thing.
Yeah, exactly. Exactly. And we're going to be probably looking at some of the image ones, but we're also going to be looking at water potability a lot because it just has really good data for this. And in fact, let me pull up the one we're going to use. Um, and we talked about these learning models just take a ton of data and feed it into this neural network that uses a bunch of statistics to crunch numbers to create, say, a binary classifier. Um, and if we look here, we can kind of get a preview of what some of this data looks like. And this is data with a bunch of different inputs about water, right? The pH level of water, its hardness, if there's solids dissolved in there, whatever a chloramine is, what the concentration is, the concentration of sulfates, conductivity, carbon. So each of these would be a different input in our input layer of this neural network. And all of these numbers would be put into our learning model as we train it. Um, and then we would ask it at the end of the day to spit out and let me get a little more room here so we can see. So we can see there's a lot of data here. And then at the end of the day, we would want to get spit out somewhere in here should be hiding the actual output. There we go. So, and let me grab an annotator. Like we could imagine as like a really simple example, we're feeding all these inputs in here from this row, right? And this is like one water measurement or something. And they're all fed in, and then we get at the end of the day our number, right? That represents if our model thinks this water is potable or not. To do this, we have to work a lot with lists and a lot with matrices or matrices, which are just lists of lists. And to do that, we're going to need PyTorch for other reasons as well. But let's take a look at this and see what this looks like. And give me just one sec to pull up my notes here. So a matrix is basically a list of lists. And I don't need to use PyTorch to make one. I'm going to use the random library to help me get some random numbers. And I could make a matrix using a Python list comprehension just to get me some numbers to play with. And this list comprehension, we don't have a matrix yet because we don't have a list of lists. But I've list comprehension generated 3 random numbers. But a matrix is a list of lists. So I want 3 rows of 3. So I'm going to actually take that and do another list comprehension. To build that out. And I'm going to also import from the pretty print library, we'll import pprint so we can see this printed out a bit more nicely. And now we can really see our 3 rows of 3. Right? And we would say that the shape of this is 3 by 3. And we would say that it has 2 dimensions, right? And you can think columns and rows. And let's just make another one. And let's just go ahead and print both of these out. And again, we're not even worrying about PyTorch yet, but you can see how we might represent all sorts of data this way to feed it into some sort of learning model. Now, the challenge here is like when I want to start manipulating this, like maybe I need to multiply this value here in the first one by this one, and then the second value over here by this one, and this one by this one to form a new list, right? And to form a new matrix that has like the product of all this stuff multiplied together. And we can totally do that in Python. It is a bit of work. I'm going to make a list to hold my result. I'm going to need to do some looping. I'm going to loop through that first matrix. And I need to grab its length because we're going to need to do some pointer stuff. And in fact, I'm going to need another list sort of for the sub results of each of my multiplication steps. And let's just print out just to make sure my code is working the way I want to here. Let's just make sure that we're printing out all the things in each of these matrices. And I see that here I've got something from the first matrix, from the second matrix, right? It might be easier just to print out one of them. And I can see that indeed I'm going through my first matrix one thing at a time, right? But now I need to kind of do my multiplication. So I don't want to print stuff. I want to multiply and add it to this list here. And we're going to build this guy up and then stick it in the result. So I need to do something like this. Grab the first row and column, rows zero, column zero from matrix one, and multiply it with row zero, column zero from matrix two. And then once I've done that, I need to append that new list to my sort of master list. And then finally, when we're done, we need to print the whole thing out. And fingers crossed, if I didn't make any errors here, um, we're just gonna have to trust that I got the multiplication right, but we multiply 0.2 by 0.08 to get us this 0.235 value, and so on and so forth. And we've done a kind of matrix multiplication. And I know that the long strings of decimals can be intimidating, but I just wanted to show this with non-integers just so we can kind of see different ways of doing things in that nice list comprehension. So this works fine, but this is an awful lot of work. It's easy to screw this code up. What if I make a mistake? And if I want to do more stuff, it becomes even more work. And we need to do stuff like this all the time, right? Because my learning model takes in all these different inputs in, say, the input layer, all these different data points that might represent, different water potability measures from one measurement. And we gotta feed them all in to all of them. And then I have to do it with that one as well. And then for this next layer, it would be the same, where for each one of these, it needs to go into the next. And so just in terms of representing all this data, and I realize this is a terrible diagram, but does this at least capture the idea of like each node, sends its data to all the other nodes in the next layer? Perfect. And thank you for the thumbs up. And now we can banish the terrible diagram. I wish there was a way to do a TL draw overlay. We can see how this matrix, right, this list of lists is really useful for this. And we're going to have to do a whole lot of list manipulation. And that's where PyTorch comes in and something called a tensor comes in. And a tensor it's a class, basically. You can think of someone made a class tensor, and it sort of generalizes matrices and vectors like this, and lets us even have more dimensions, right? If our lists are of let me kill the annotator. If these matrices are two dimensions, right? Because we have a row and a column, we could imagine a three-dimensional matrix that might look like this. Let's see if I can get this right. I'm going to make a really small one just because otherwise I'll get lost in the sauce. And I think, in fact, what I'll do to help me visualize it, because otherwise I'll lose my mind, is something like this.
You started your variable with a number and it's mad at you.
Thank you. And let's see if I have this right. We've got rows, which is dimension one. Each of those has a column, which is dimension two. But each of those columns has something inside it, which is dimension three. I think the test here will be the pretty print. And the shape here should be 2, 2, 2, where we have two rows. Each row has two columns, and then each column has two things in it. So, right, three dimensions, and this is the shape of that matrix. And if I print this out and we scroll down here, um, I'm not sure why Pretty Print didn't put it on separate lines. Maybe because the matrix, it doesn't take up enough space or something. Um, but hopefully y'all can kind of see what I'm driving at here. Does that make sense? Though we didn't get the nice the nice printout, but you can kind of see it visualized here, right? And if I really wanted to, you know, we could maybe visualize it like this. Where you can now you can see that three levels of nesting basically, and it looks like there's something extra that got added along the way. Let me just fix that. And and that's our three dimensions. And I'm missing a closing one right there, and that should do it. Right. So the term is dimensionality, but I think rows and columns, and frankly, I do a lot of counting and highlighting and pointing. So you could imagine how for a learning model for water potability, we have all those different factors. We have a lot of dimensions. So all of a sudden we need to do all sort of like matrix manipulation. And so a tensor lets us do all this and does all this work for us. And let me show you what I mean. And I think that's going to be the best way to see it. And let me add a markdown here. So a tensor is an easy way to represent matrices and have access to matrix manipulation, like mathematical functions. I think you'll enjoy it once you see it because it's honestly pretty cool. So I've imported PyTorch already, and I'm going to go ahead and make a tensor, and we're going to have the first row or dimension will have three things in it. Let me do this 4, 5, 6. And let me make two of these things. And you can sort of see how the different positions of the two tensors match up. And it looks like I have a typo right here, and that should be a comma. And if I print out tensor 1, and then we print out tensor 2, let's see what these look like. So this looks pretty straightforward, right? It's pretty similar to the matrix we made by hand. So we haven't quite seen the benefits of our tensor manipulation yet. But let's do that same matrix multiplication, but with tensors. And actually, let me write it like this. So just like I would multiply two numbers, I am going to multiply our two tensors. And now let's run our Jupyter notebook. And what we see over here is pretty nifty. It takes 1 and multiplies it by 9. It gives us 9. It takes 2 and multiplies it by 8 and gives us 16. 3 gets multiplied by 7 to give us 21. 4 by 6 to give us 24, and so on. Right? And it does all the work for us. I don't have to write all that code. And, I'm lucky I didn't make more errors writing that than I did. So tensors are these Python classes that have all of this built-in matrix manipulation math. We can also do tensor addition. And I'll just say like tensor multiplication and tensor addition. And you can sort of use matrix and tensor synonymously in this case. And over here we see all these added up. And since 1 and 9 add to 10, and 2 and 8 add to 10, and 3 and 7 add to 10, and in fact, all of these add up to 10, we can see that our tensor addition is doing its job. So I just want to pause and check in and see if folks have any questions thus far.
So the using the torch.tensor basically makes it so you don't have to write all that out and have like a tons of line of code for doing that stuff.
Exactly. And there's a whole lot more that we can manipulate tensors that we're about to see. So let me show you some more things that you can do with tensors. Let me just go ahead and print tensor1. I can also use a tensor function called view to reshape this tensor. And right now, remember, this is essentially 3 rows of 3. Let's reshape it to be 9 separate rows that each have one thing in them. And so here's my original tensor. I had 3 rows of 3, and now I have 9 rows of 1. And the original tensor is exactly the same. It has not been modified, right? And this gave us something new. We could also reshape it using a view to look like this, where it's just one row of 9 things. Right? And so again, this is all this manipulation of the matrices that the tensor does for us. And the original tensor is unchanged, which is really useful for a learning model where we might need to do back propagation and tweak our biases and weights based on, how well our model identified a picture of a cloud or if this water is potable or not. So the tensor, it can hold on to different shapes of the same thing. And it will, in fact, keep track of the changes that we've made to it, though we won't really see that today. And we can see here the original tensor is unchanged. And I just want to pause and check in and see if folks have any questions. How are we doing?
So to be clear,
Yeah.
let me just say node would be being multiplied by a bunch of other like neurons. So this would keep track of like if there's like 6 others, 6 different things multiplying against it.
Yeah, exactly. Like, let me just go back to the diagram because this is a good diagram. So, right, for water potability, there were I think 8 different factors. So we might have 8 different inputs here. And let me pull up the annotator. Well, I'll just draw a couple more. Right. And then for each layer that does some sort of statistic mathematical operation to the data. Each node or neuron sends all that information to each of the next nodes in the layer. I think this one is meant to point to this last one here as well. It just might have made the diagram too confusing. I'm not totally sure. And so you can see how like using a matrix to represent this is really useful. And we keep kind of doing statistical stuff until we come up with a number. And depending on if that number is good or bad, we tell the model, and the model kind of works backwards and then tweaks stuff to try and like make it do a bit better. And we do that about a couple thousand times, and then we end up with a decent model. Though I realize, I've been doing a lot of hand waving about the statistical stuff that each of these neurons does, and that's what we're going to get into more next week, right? And we're going to dig into that. So we're not there yet, and I don't want to open that door yet. Does that help answer your question a bit, though?
I have another quick question.
Yeah.
This might be like out of scope somewhat, but say we're doing like a problem and we're not really doing anything with AI, but the problem has like a lot of math. Like this, tensors would work for that too, then, right?
Yeah, absolutely. And I think they do get used for a lot of scientific computing stuff and other things. Yeah, they totally would work for other stuff. We're not going to use some Python libraries, like there's one called Pandas and NumPy that get used for a lot of data science and scientific computing that also get used in machine learning. Though PyTorch does use them under the hood, I think. So yeah, tensors, you can use it for anything. And in fact, the book that you have assigned reading from for homework, which I think this is some of the most valuable reading you can probably do in the whole course. This is the book we kind of use to help design this. And it goes really, it talks a lot about PyTorch, and it's just really cool. It also has, in Jupyter Notebook form, all of the code examples that you can code along with as you do the reading in the book. And this is, I think, really going to be mainly what we do as opposed to assignments. So you can kind of see what's happening. And this is obviously just a lot of output printed out. But this is a Jupyter Notebook, so you could actually clone this and then run this on your computer. All that's down the line, though. And it's a great question. Let me continue on with tensors, because there's a lot of good stuff to see here. And I want to make sure we hit the key things. I can also slice tensors. In a similar way, I would maybe slice a list. If I run this, what we see, and let me just go ahead and print the tensor one so we can see the two together. It grabs everything from, man, let me see if I make sure I get this right, because this I think is always tricky. It's grabbing the second thing. If we go index 0, index 1, from each row, right? For each row, it's grabbing the second column. And if I change this to, say, 1, 1, we would only grab from the second row, the second column, right? And 2, 1 would give me that. And conversely, 2 colon should give me row 0, row 1, row 2. Right? So we can do all these slicing operations. And today is more of an overview. Don't worry about memorizing each of these operations. A few of these you'll use a good amount. A lot of these you'll use a little. Some you might not use a lot past today. the goal of today, I think, is to really get comfortable with tensors and the different ways we can play around with these matrices, if that makes sense. In addition to slicing, we can do some filtering the same way. And so I can get all of the values in tensor one that are greater than 5. And it looks like I have a typo here and a typo here. And note that this new tensor has a different shape, right? And in fact, I think the shape would just be 4. It's got 4 rows. If I was to pretty print this, I guess it still prints out on one line, but each of these is actually one row. And we would say this is either 0-dimensional or 1-dimensional. But so we can filter tensors as well, which is honestly super cool. I can also combine tensors together or concatenate them. So I can take tensor 1 and tensor 2, and I'm putting them in a little tuple here. And if I had more, I could do tensor 3 and so on. And we're going to combine them into a new tensor. The original stand changed. And I can tell PyTorch how many dimensions I want this new tensor to have. And in Jupyter Notebook, I can, if you just, it will just print out whatever the value of the last line is. So this should print it out. So I'm just, for simplicity, going to ignore the print statements. And so tensor 1 was 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Tensor 2 was 9, 8, 7, 6, 5, 4, 3, 2, 1. And it's just stacked them together. And here we can print tensor 1 and let's print tensor 2 as well so we can see all these compared. And so tensor 1 was these 3 rows, right? Inside a list, list inside a list. Tensor 2 is the same. They've been stacked now so that we've got 6 rows of 3 with a list inside a list. And it gets interesting if I start to play with the dimensionality. And I'm not going to lie, I do find this a bit tricky to keep track of myself. But if we run this, what we now see is that we have 3 rows of 6. And in fact, I have some notes on this that I'll pull up because I do find this confusing. What we're doing when we change this is we're telling PyTorch where to add the extra layer. And I think if we go from 1 to 2, I'm not sure if it will work. Yeah, and indeed we get an error because we can't combine them in that way.
Wait, so to be clear, the first dimension is just setting up the list of lists up and down. Second dimension is going sideways. Would that be accurate?
Yeah, let me pull up my notes because I was going over this before, and I'm not gonna lie, I do find this confusing, but it does touch on a good point. Um, give me 1 second. So, hmm, let's see here. The dimension over which the tensors are concatenated. Yeah. So this is the tricky bit. This first one here, dimension equals 0. So our first dimension is our rows, right? We have 3 rows here in this outer list. And so when we concatenate, we combine and put everything in the outer list. And I think this may be what you were saying, right? So I'm taking each of these and I'm putting them all in the outer list. When I go from 0 to 1, I'm saying, you know what? When you combine these, don't combine at that outer list level, go one level more. This next level in, this inner list, our columns, combine stuff there. And so here we see 1, 2, 3 from tensor 1 up here gets combined with 9, 8, 7 from tensor 2 here. So it's confusing because I keep thinking the dimension works in a different way than it does. It's telling us which level it's going to do the combining. Does that help a bit? Yes, sort of. Yeah, it's honestly, I think this is a tricky one, and this is also why I don't want to get too lost in the sauce on this. And you guys won't have to do tons of serious tensor manipulation, so don't stress out too much. Let me just, I think, point out one more time what's going on here for illustrative purposes, and then that'll be good for us to move on. So we're combining tensors, and I'm saying don't do the concatenation at the outermost level. Do it one level in, right? Don't put everything into our outer list. Go one level in into this next list in and do your combining here. And so this 1, 2, 3 from one level in on tensor 1 and 9, 8, 7 from one level in on tensor 2, they get combined here as opposed to the other way with dimension 0 where they all get combined at the outer level. And this 4, 5, 6 and this 6, 5, 4 get combined here. And then these get combined here. Again, today is more of a preview. And again, to be totally honest, I had to spend a good amount of time drawing this out, playing with a large number of examples and talking to ChatGPT and the internet. And as you can tell, I still find it a bit tricky to describe it correctly. So really, the homework is going to be the reading, which is going to be really good, but just playing with tensors. And I'm going to give you all this file to play around with. And we're not going to have to get too crazy with the manipulation, but I do want you all to see how there's different ways we can combine these things. I think that's the main takeaway. So let me show some more ways that we can work with and manipulate tensors. We just did some concatenating. Sort of the next step up from concatenating is something called stacking. And again, we get to have some say in how they get stacked. And let's start this out actually at dimensionality 0. Apologies, my mouse is being a little frustrating. So here we see tensor 1 whole and complete, right? Our nested list of lists, and tensor 2 whole and complete, our nested list of lists, just stuck inside another list, right? You'll see what I mean? So we just literally combined these two things into one bigger tensor. And if I wanted to combine and stack them in a different way, what happens here is we grabbed the first row from tensor 1, the first row from tensor 2, the first row from tensor 3, the first row from tensor 4, the first row from tensor 5, the first row from tensor 6, right? With 0, we just stacked the whole thing on top of each other. With dimensionality 1, we kind of went inside. And again, this is an awful lot to absorb, and don't worry too much if you feel like you're not tracking how each piece moves. Again, I think I want the main takeaway to be there's a large number of powerful ways for us to manipulate these matrices. Before I kind of move on and show some other tensor stuff, I do want to check in and see what questions folks have, if there might be some good examples to play around with. And how are we feeling, by the way? Like, are our brains fried? Do we feel like we're sort of tracking, or do we feel lost in the sauce?
I'm tracking this. I don't know if I have special brain or something, but this makes sense to me.
Okay, awesome. Glad to hear. It always takes me a long time to learn stuff, to be honest. I'm really slow at learning certain things, and then it finally clicks. And it took me a long time to get this one down. But the pieces are always simple, but then when you put them all together, we get the complexity. And also, it's just super cool, I have to say, because of like, imagine an image file, which is basically just a big matrix of pixels, right? And think of all the ways we could mess with an image file with tensors. So let's see some other let's see some tensor methods, in fact, and I'll just put a little message in here. So there's a number of tensor methods. There's size. And remember, I was talking about tensor shape. And in fact, let's go ahead and let me print tensor 1. So size, when you hear tensor size and shape, it basically means the same thing, right? 3 rows of 3. And we could say this has 2 dimensions. There's also, in fact, a number of dimensions tensor method. Or rather, it's a property because we don't have to call it as a function. And here, my tensor has 2 dimensions, right? And if I was to do, tensor, I'll print that out. Tensor 3D equals torch dot tensor, and let's see, something like that. Um, it gets a little tricky to write it out. If I was doing this for real, honestly, I would put this on multiple lines to make it easier. But I think I now have stuff right. So let's print tensor 3D and see if it's right. And so we've got a tensor of 3 dimensions where we have 1, 2 rows, but then inside this row, well, there's only actually 1 column inside there. So it's not perfectly organized, but then there's 2 things inside there as well. And if I got that right, if we look at the number of dimensions, it's 3 dimensions. And if we look at its size, I think it's going to be 2, 1, 2. Oh, and it's 2, 2, 2. Because in fact, I did build it right and then confused myself and thought I got it wrong. We have 2 rows with 2 columns in there, and each column inside that has 2 rows. We can also look at tensor types, and this actually you will use a lot. Like number of dimensions and size, you all will actually use a lot. Because as you saw from that diagram with the learning model, really the task is like, I might have like, a 3-dimensional tensor, like a matrix with 3 levels, but I need to quash it back into 2. And eventually I need to crunch it all into 1 number for my binary classification. And tensors do, I believe, have to have all their values be of the same type. And here, we can see that our tensor that we made is integer type. And if I made a tensor float, and we print out, and let me put that in a print so it'll say it. And we print out our tensor float data type. I believe we should see float instead of int64. Yeah, and a 32-bit floating point number. Right, and that matters, right? If all of my data is this integer type for this math that's a bit more intense, I need to make sure that I stay in that realm. But if I've got a bunch of floating point numbers, I need to maybe do some conversion along the way. So out of everything, like these are actually kind of the most useful things probably that you all be using. There's also something called unsqueezing a tensor, which is kind of a counterintuitive term, because we will in fact add another layer to it. And here, let me print tensor 1, and then we'll print what happens to it when it gets unsqueezed, so to speak. And you can see that it's a little hard to see, but there's 2 angle brackets here, and here there's 3. It's literally just added an extra angle bracket. And it's done it at the top level of the rows. And if I change this, it adds the extra level in here, right? Now there's an extra level here, there's an extra level here, there's an extra level here, right? We had to do it at a layer in, right? Do we unsqueeze it at dimension 0, dimension 1, or dimension 2, where everything now gets an extra layer? There's also basically the opposite of unsqueezing, which is raveling, where we basically get rid of layers. And this one I think is fairly straightforward. As you can see, it's just gotten rid of layers. And now we just have a one-dimensional tensor or a list like we're used to seeing. And again, this is a lot of stuff. As I said, this is new to me. It took me a good amount of time to play around with this stuff, to get comfortable, and I still feel, a little rough around the edges with some of it, to be totally honest, but it's pretty exciting. We're almost done. There's just a few more things I want to show. We can also reshape tensors. I want one row of 9 items. Maybe I want 9 rows of 1 item. And I need to put tensor 1 because that's our tensor that we're reshaping. Now, because it's 9, I can't really do like 2 rows of 4 items because there's 9 things. And so the shape of the tensor matters for what we can do to it, right? Now I can do 3 of 3, and that's in fact the original shape of our tensor, right? So the shape really matters in terms of what we can do to it. There's also splitting, where I'm going to get a tuple. Right? And we've grabbed, this is what was the second row of our tensor. And so again, here by playing with the dimensionality, I could slice it even finer, depending on, maybe I don't want a whole row. Maybe I want an individual item within the row, like a dimension down. And then there's things like addition and summing and getting averages. And this literally adds up all the numbers in the tensor. And similarly, we can get the average or the mean, which is all of them added together and divided by the number of things. And it looks like I have a typo. Let's see what I did wrong. Could not infer output D type. Let's see what we can do here. I suspect I may just have to do some casting. I suspect because I built my tensor with integers, I may be running. Yeah. So if we look at this error message, the mean to add everything together and divide it by the number of things to get the average only works with the floating point type, right? But I built my tensor as integers. So this is a problem. So instead, let's just make a float tensor real quick. We'll just do 1.0, 2.0, 3.0, 4.
Can you not just cast the other tensor as a float?
I could. That is a good point. I actually don't know how to cast a whole tensor. Cast float. Let's see what this does. It looks like it converts. This may do exactly what you were saying, Jack, which would be awesome. Let's see if this works. Tensor dot one dot float dot mean. Oh, and I probably need to print it. But it didn't air out, which is a good sign. And I'm going to trust that that's right of adding all those numbers up. And I think it is. Yeah, great call, Jack. Thank you. Right, so that's cool. We just casted the value of everything inside here to a float. Let's see. There's one or two other things. I think we've gotten a lot of it, but we can also find max values. Um, and let me, in fact, print out tensor one. And now let's print out max value, and let's print out max index. And we can see what this looks like. So this is kind of interesting, right? Because what max did is it returned the tensor with the highest cumulative value, I believe is what it does. And then it gave us, it looks like, the index for each item in the tensor. And this one, I'm not gonna lie, I'm a little rusty on, and I'm curious if we change this to 1, what happens? And so that was really interesting, because look what it did. We shifted the dimensionality up, and dimension 0 was grabbing from these. But now at dimension 1, it's going inside here, and it found the biggest here, which is 3, the biggest here, which is 6, and the biggest here, which is 9. Now, why the max? I'm not quite sure what max index is doing. I think it's doing something different than I thought it was. But max value, we can kind of intuitively see what's going on. So again, there's just so much cool stuff that we can do with this, and we won't have to do tons of this. We will definitely have to do some. But some of this PyTorch will be doing for us. We can also do what's called transposing a tensor.
So I looked it up and you were right. The twos, it's just the indices that are the highest value.
Oh, oh, you know what? Oh, this is tricky. That makes sense. So dimension 1, index 2 is inside here. So what is it, like 0, 1, 2, and then 0, 1, 2, and then 0, 1, 2. And if we change this to min, which I'm sure this must have, Does it all become 1, 1, 1? Well, 0, 0, 0. Yeah, that's cool. Thank you for looking that up. Yeah, that's tricky. I think that's what's going on there. So, as you do this stuff, you're definitely going to have to do some reading of the docs and experimenting. I think is the best way to see how this stuff works. Transposition, I'm not entirely sure what we're doing to the tensor here right now. To be honest, it doesn't make a massive change. I think the last two things I want to show are, let's see here.
Oh, with transposition, you're turning all the rows into columns and all the columns into rows.
Oh, oh, I see what you're saying. I totally missed that. That one was staring me in the face. I love it. All right, let me print out that and let's print out. Yeah, good call. That's what happens when you stare at a screen too long. Yep, you're totally right. And that's pretty cool. We had row 1, 2, 3, 4, 5, 6. But if we look here, our column is 1, 4, 7. And indeed, that's been transformed into a row, which is honestly kind of awesome. And then the last two things are normalization. So often input data needs to be normalized before we can feed it into our neural network. Normalization could mean a range of things, but I think you can all see how, we just can't stick any number in here. I might have to cast everything to a float. Maybe we don't want negative numbers and they have to be converted to some sort of positive value. Maybe I need every number to have not more than 3 decimal places or exactly 3 decimal places, right? There's a also, frankly, if we're getting like, raw data, we could see lots of spikes. If we're looking at, think about a heart rate monitor, right? And we have a bunch of data about my heart rate, and over, a 1 hour period, maybe there's all these little spikes and stuff that aren't very useful that could mess up the model. So we kind of have to soften the data to be more of an average, if that makes sense. So normalization can encompass all these different things, and we can do this with tensors, obviously. And we'll have built-in functions for this. I'm just going to call this my tensor, and let's make a tensor that is just 1.0 and 2.0 and 3.0 and 4.0. And actually, oh, sorry, I got a little lost in the sauce there, folks. We might want to, let me type this out and then we can walk through it. So, and we'll just call this tensor. So I'm not sure I have.
On line 1, you have an extra bracket that's causing it to mess up.
Oh, thank you. There we go. Good call. Let me run this and then we can talk through it. So I also want to make sure I got this right. So normalization is a sort of like a standard mathematical statistical thing. And to be honest, I think I'd have to look it up. So yeah, it's adjusting stuff to a common scale. Do they have a standard normalization function here? I think there's different ways of normalizing. I think what we're doing here is something involving like looking at changes from the standard deviation. If we look at what's going on here, we've got the tensor minus the average value of the tensor divided by the standard deviation from the average, which I think gives us some sort of interesting measure of how much change one value has from another. And I do apologize that I'm doing a little bit of mathematical hand waving there. And actually, if someone wants to maybe share a better description or look a better one up, that would be good to see.
I can add
Yeah.
to it. So for the normalization, you're calculating a z-score so that you can use the normal distribution. So if you
And
Google z-score,
what's a z-score?
have you seen the bell curve? Which is the normal,
Yes.
that's the normal distribution. So you're basically calculating where on that distribution you fall.
Rachel,
So
thank
like,
you so much.
yes.
Yeah, so in fact, let me just. So in essence, where we're assuming that, and Rachel, tell me if I have this right, that the majority of our data points are going to, that are, we're going to have a range of data, and most of the data is going to be in sort of like an average range.
Yeah, so for the middle would be 0 where the line is, and then you would have like a -1, a -2, a -3, and then a 1, 2, and 3 on either side. So it says like 68% of data points are within one standard deviation. That would be the 1 and the -1. And then for the 2 and -2, it's the other way.
Okay, that's
And is
awesome.
this showing like how far off they are from that?
You can see like what percentile you fall in. So you would expect like the majority of your data to be between 3 and -3 standard deviations away from the mean. It's very statistical.
Yeah, machine learning is mostly statistics, and I am going to be brushing up on this stuff more. I feel like I have new statistics once, but never that well. So it will be new for me as well. I wonder if we can find a better image here. This is probably a better one. Yeah, so I think in essence, when we're normalizing our data, we're kind of tweaking it to fit it along this curve, if I have that right, Rachel, so we can see how much variance there is.
Yes, but like depending on your model, there's different normalization techniques, so you might not always want to use this one. Like if your data doesn't follow a normal distribution, then you would use something else to normalize, a different distribution to normalize your data.
Right, right.
But most of the time, like we use this one.
Have you done some machine learning stuff before, I take it?
Yes.
Oh, that's
Like
awesome.
mostly the statistics side of it, like more with the algorithms. Like, so rather than using PyTorch, we would like use NumPy to do the algorithms by hand so you can like see the math.
Mhm. That's awesome. What was that for, if I may ask?
My degree is in analytics, so I know like the math and statistics behind a lot of the algorithms, but not as much of the code.
Got it. That's awesome. I had not realized you have a degree in analytics. Um, is that a math degree? It's not informatics or something like that?
So I actually got my undergrad in operations research, which is a lot of math, and then I got my master's in analytics.
Ah, that's awesome. Operations research, I'm vaguely familiar with. It seems cool, though, from what I understand, it's actually a lot of math. Analytics is actually new to me, so that's something for me to look up. That's really cool. Cool. Well, I may be asking for your help at a couple points over the next week. Um, okay. I think this is probably a good stopping point for us. There is one last sort of feature just to demonstrate here, as long as we've gotten this far. Something called broadcasting. And Rachel, thank you again. I'm a huge fan of like, man, like we all have a pretty wide range of experiences. So whenever, someone has some like knowledge to bring to the table, I feel like that's a win for all of us. And if we put these things together, so if I fix my spelling mistake and let me full screen this. So the thing is that these tensors have different shapes, right? This one just has a shape, I think, of 3, and it has 1 dimension. This one has a shape of 3, 1, 3 rows of 1, right? I didn't write it out row wise, but here's row 1, row 2, row 3. And it's got 2 dimensions. In when you see the term broadcasting, think expanding. And it looks like I'm actually not sure how it's come up with these values. Um, but I think it's performing some addition in some systematic way. It's probably in fact taking, yeah, it's probably, and Rachel, you might be able to tell me if I have this right. It's just adding each element to each other one to give us 2, 3, 4. And then 2 plus 1 gives us 3, 2 plus 2 gives us 4, 2 plus 3 gives us 5, and then same here with 4, 5, and 6. And so we will probably be doing a decent amount of this as we build our learning models to help shrink or grow the shape of our tensor as we need to, as it moves to the neural net. All right, that was a lot of stuff, and I appreciate folks sticking around. Hopefully people are getting excited about this. Remember the goal here, we don't have to become experts in all of this, and also none of this is actually on any of the graded assessments. One day we want to do that, but the goal here is really to peek under the hood to this really powerful technology, and hopefully then maybe use some of this in your personal and group projects, as well as give you all some foundational skills so you can go out there and leverage, there's 1,000 already trained learning models out there, right? But I think the more you peek under the hood, the easier it becomes to use them. What questions do folks have before we wrap up? Okay. How are we feeling? Pretty good?
I guess I just feel like I'm not really seeing the big picture of this yet, how
Yeah.
it's going to integrate into whatever we're going to do later.
Yeah. Honestly, the AI module is pretty separate. It's not really integrated into the rest of the curriculum. We eventually would love to have you all build a full stack application that uses either a pre-trained model or a model that you train, but we haven't gotten there and that might be too much. But if you imagine, think about a website where or just imagine your Netflix and you want to like see if someone writes a bad review of a movie. And if so, you want to not recommend other movies by that director. How do I know if a movie review is good or bad? I would have to do some sentiment analysis of the review I wrote. Or if I want a website where I can upload a picture and someone tells me if it's a slice of pizza or a bagel. And so I might have a web app that then talks to some sort of AI model that I built. Doing all of that is kind of out of scope of this course, though we're kind of slowly getting there over time. Um, and again, the goal here, I think, is really to peek under the hood and learn how this engine works, because this has become such a fundamental technology. And so next week, we'll start to learn how to build a learning model and a neural network. Each of these nodes is basically, from what I understand, going to be a tensor. Right. And so kind of the overview today was peeking under the hood of what's going on here in terms of how all of the numbers representing our training data get manipulated. I don't know if that helps at all, Jason, because I think that's a very understandable question.
I'm good.
Cool. Yeah. Big picture, again, we're going to be writing object-oriented code. We're going to be using Python, but this is sort of a separate independent module. And the goal here, technologies come and go, right? There's a lot of languages out there like Python. There's a lot of web frameworks. They come and go. Web application architectures stay the same. Concepts stay the same. Object-oriented programming has been around for ages. Once you learn one object-oriented programming language, you can learn another more easily, right? And so in software engineering and computer science, concepts are really the keys to the kingdom to learning and growing and having a long career. And this AI stuff isn't going anywhere. So we want to give you all some fundamental concepts. The reading is really good. Please do the reading. I know it will take some time, but I highly, highly recommend reading chapters 1 of this book, and chapter 2. Chapter 2 is going to be a bit bigger, but I would say get as far as you can, and we'll be kind of moving into that territory next week. This article is honestly exceptional. It's like a huge high-level overview of machine learning and deep learning. And while it might not be extremely technical, it uses an awful lot of jargon. I think it's a great article. On a practical level, I would say maybe start with the book. But again, our goal here is to get our hands dirty, to learn some of these concepts to what's basically become a fundamental technology for software, which is AI and generative AI. On that note, let me stop the recording and let's wrap up. Oh, James, yes, sir.
Yes, I would just like to add, these are some good readings, but I would recommend not reading any of this until you've completed your OOP assessment. I
That,
would recommend that you continue to focus on OOP.
thank you. Yeah, I totally forgot to mention that. 1,000% what you said. And we'll have a review tomorrow for object-oriented programming, and you'll have the assessment over the weekend. So you know what, James, you're right. As much as I love those readings, like keep charging on OOP, and we'll pick up the AI ball on Monday. All right, folks.